So we're going to talk about sets today. Before we do that, though, we're working on an assignment, right, for Thursday. Anybody got questions?
Yes.
Yes.
Can you clarify question 4?
Yeah, okay, so question number 4 is in 2 parts, right? In part 1, part A, where you're going to find 2 even integers whose sum is not a multiple of 4. There are infinitely many pairs that will work. If you start with any even integer at all, you can find another even integer to pair with it that will satisfy this. So you just want to add up 2 numbers, 2 even numbers, and then check. And as soon as you find a pair where the sum is not divisible by 4, just say, okay, there it is. And then there's nothing to write. Just say, here it is. 2 even integers, these add up to this thing, not a multiple of 4. Done.
So 4 plus 6 is 10, and that's not divisible by 4.
Right. Like there's one. There's infinitely many others that'll work too. Okay. This is to get us ready for 4B, which in 4B, you're presented with a quote-unquote proof that the sum of 2 even numbers is always a multiple of 4. We know that that's wrong because we found in part A 2 even integers whose sum is not a multiple of 4. So the idea with part B is to figure out what's wrong with that proof. So let me see. Oh, wait, wrong course. Sorry, hold on. So the proof says let x and y be even numbers, then x is 2m and y is 2m, where m is some integer. So then x plus y is 2m plus 2m. 2m plus 2m is 4m. 4m is a multiple of 4. So we know that there's something wrong with that proof because the statement's not true. So we just want to point out with the error. There's like a flaw in the logic. And we want to figure out where it is.
I know you want us to use this sheet as a cover sheet. Can we write notes on it or no?
I mean, you can write some notes on it if you want, but I'm not going to use anything you write on the cover sheet as part of your work. Yeah, that's okay. Yeah. Does that clarify what you're being asked to do? Do you have an idea of how to proceed, or?
Not directly or contradictory, just straight.
Just like you're not really writing a proof for part B. What you want to do is point to something and be like, that's the problem. We can't say this statement wherever here. Like we're not allowed to say this, or this is more than we can assume, or something. Does that make sense? Okay. If you're still stuck, let me know. If you're not sure, if you can't seem to find the error, let me know. Because I'll tell you, 2m plus 2m, as a math expert, trust me, 2m plus 2m is in fact 4m. So you all know that anyway. And if m is an integer, 4m is a multiple of 4. So the flaw is not in that line at all. All right, so it's a short proof. We know that the algebra they did at the end is good. So it's got to be somewhere before then. Okay. Other questions? Sometimes I get nervous when people don't have questions because I feel like it might mean they haven't tried them yet, because usually I get questions. So are you sure there's no questions? Everybody's pretty much done? We know exactly how to proceed?
Well, I'm just a little stuck on 3, but I'm working
On 3? Okay, so if you feel like you have a path forward, that's good.
Maybe.
Maybe. I mean, you're proving it directly, so how do you start that kind of proof? How did you start that proof, Wes? Wes?
Let me see, what he's saying. I didn't get really that far.
Okay, well, how would we start it? We're proving it directly, so.
You would create an equation that would be true if that's true.
Sorta. I mean, you might be beyond the starting point. I really just mean, like, what should our first sentence be?
We say n is odd.
Yeah.
Assume n is odd.
Assume n is odd. What does that mean?
And is odd.
Yeah, what does that mean?
And got picked on in school.
Ha.
Then 3n plus 7 is even?
Well, we hope to be able to say that,
Yeah.
but we're a ways from that.
2k plus 1.
Yeah, n is odd. We can write it as 2k plus 1. Yep. And what has to be true about k?
An integer.
Yeah.
Yeah.
Okay, there's our starting point. Hopefully, there's some more math, right? Some more stuff you're going to write. And then we hope to be able to conclude that 3n plus 7 is odd. Even, rather, yeah. If you're going to conclude that 3n plus 7 is even, what does that mean? Like, what do we want to be able to write it as?
3 times n plus 7 is even?
Well, not if it's, I mean, if it's something's even, what does an even integer look like?
It can be divisible by 2.
Yeah.
2k.
2, yeah, only this time it probably won't just be k, but 2 times something we know is an integer.
Yeah.
So somewhere before here, you know, we're going to say, oh, this is going to be, you know, 3n plus 7 is 2 times some integer. Okay, so you're going to do a little bit of algebra, might help you.
Okay.
Are there other questions? Okay. If no more questions, we'll talk about sets for a little while. So, every, you know, discrete math course and virtually any like higher level math course kind of begins and has its foundation in sets. So, a set is simply a collection of elements. There's a little bit more wordy definition here, a repetition-free, unordered collection of items. So in order for something to be a set, you just have to be able to take an element and determine, is this in the set or is it not? Like that has to have an unambiguous answer for every element you might think of. Like I could form a collection, a set of all the students at Vermont Tech. And then if you pick a random person, I should be able to determine it should be able to be found out whether or not that person is a student at Vermont Tech. So I could say, oh, you're in the set or you're not in the set. That's like a well-defined set. It's unordered. It doesn't matter the order you write them in. All it matters is what's in it or what's not in it. There's no repetition. Something isn't like super extra in the set. You're just in the set or you're not. It's like a binary condition. So when we specify elements of a set, when we list elements of a set, they go inside curly braces. Curly braces say the order doesn't matter, right? It's an unordered set. If we use parentheses, the order matters. And we know that. In fact, we see ordered sets all the time. We just don't call them ordered sets. We call them ordered pairs, and we visualize them as coordinates on the plane. We use parentheses. The parentheses there are actually important. They actually mean that it's ordered. So we use curly braces to denote elements of a set. All of these are the same set. right? If I take the elements 1, 3, 5, 7, 9 and I jumble them up in a different order, it's still the same set. If I decide to list 3 twice, it's still the same set. It's really bad form to list an element more than once, because when we talk about the size of a set, that's the number of elements in the set. There's 5 elements in the set. There's 5 elements in that set too. But in the one on the end, it's tempting to count the 3 twice because it's listed twice. So don't double count your elements. Sets can be finite sets or they can be infinite sets. So the set of all integers, we could, or the set of all positive integers, we could denote by just starting the pattern, 1, 2, 3, 4, that's a pretty clear pattern, we know how to continue it, and then end it with a dot, 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 which just indicates that that pattern continues indefinitely. When we denote sets, we can often use set builder notation, where we simply do something like this. It's the set of all, and then you actually use a variable, like x, such that, and you either use like a pipe, like a vertical bar, or a colon, like the double dots, and then just describe what property x has to have. Describe what it means to be in the set. Like, that's the generic way to use set builder notation. So in example 2.3, we're given the set of all x such that, that's how we read that colon or the vertical line. The set of all x such that x is a real number and x squared is less than 100. So what numbers are included there?
Anything that is less than 100 when you square it.
Yep. So perfect. We've kind of reworded like the description here. Can we be more specific? Like explicit about what those numbers are? 10 is actually not in the set. Huh? You're missing infinitely many values.
Yeah, anything between 0 and 9, I guess.
You're still missing infinitely many values.
Anything below 9.99999.
Now it's going to be real.
Yeah.
number, right?
That's a real number.
Okay.
Yeah.
It just can't be.
So anything, so the real numbers that are such that when you square it, it's strictly less than 100. So these are all the real numbers between -10 and 10, not including endpoints.
So not including -10 or 10.
Mm-hmm. So up to 9.9999, however far out we want to go. We could also say it's the set of all x. We could reword the condition to say that -10 is strictly less than x, strictly less than 10. So using some math notation instead of writing it out in words. We could represent it kind of graphically on the number line. And there are infinitely many values in here. Some sets are used so often that they've been given special symbols. So the real numbers, we use this. So there's this particular font that you see, the R, Z, N, and Q, is called Blackboard Bold. So Blackboard Bold R is the real numbers. When I write, there's lots of little double lines. When I just write it out by hand, I just do a double vertical and make it like that. The Blackboard Bold Z, that's the integers. Blackboard Bold N, Blackboard Bold Q, I just kind of put a little extra slash up there if I'm writing it out. So yeah, Z is the set of integers. So when we were talking about problem 3, and we said, oh, suppose n is odd, so that then n is 2k plus 1, where k is an integer. We might also write something like, then n is 2k plus 1 for some k in z, for some integer k. And as we're about to see pretty soon, well, I guess it's in a couple of pages, but I'll spoil it right now. This little symbol right there, that funky looking E, just means is an element of, or is included in.
That was Euros.
Yeah, it looks kind of like the euro sign. So we could rewrite that symbol above, the one, or the set above, the one we're talking about with the integers, such that when you square, it's between, it's less than 100. Yeah.
Dumb question. If you go up to the little graph drawing you're drawing
Uh-huh.
of the set, does the 0 mark need to be there?
No,
Okay.
I just usually include 0. I don't know why, but it doesn't have to. Any 2, once you fix 2 points on a number line, like your set, everything is sort of measured in that scale. But
Zeros are important.
I think of 0 as being kind of important, but. So if we wanted to rewrite that set, we could say it's all x in the real numbers such that -10 is less than x is less than 10. Kind of just specifying. Instead of saying x is a real number in English, we kind of shortcut a little bit. Oh, I guess I did already introduce that symbol. It's right in the definition. Good. Okay. All right. So we have some special sets. The universal set we denote with a capital U, and that's just the universe. It's like all the things under consideration, and it's often context sensitive. So if in number theory, the universal set is usually the natural numbers. In calculus or pre-calc or algebra, usually our universal set is all real numbers. And we might consider the set of those, that in that first example, those odd single-digit integers that we're looking at, we might consider them to be a part of the universal set of integers or natural numbers. But often it's context-driven, or if not, it'll be, might be given explicitly. But it's just sort of like the universe. It's everything. The other special set is the empty set. It's the set that has no elements. We denote the empty set with a little circle with a slash through it. In some texts that you'll check out, if you're looking at other resources, they might just denote the empty set as just an empty brackets, like a set of curly braces with nothing in it. That's less common, but it's not rare. I've seen it happen. This is far more common to use that little circle with a slash. So, let's do some operations on sets. First, we have what we call unary operation. A unary operation is an operation that is performed on one item to produce another item. So in this case, an operation we can perform on one set to produce another set, and that is the complement. We're going to use the little prime notation, like this little kind of tick mark at superscript, to denote the complement of a set. And the complement of a set is everything in the universe that's not in your set. Depending on the book you look at, you might see them use a little overline or a superscript C for the complement. So suppose our universe is the set of natural numbers, and A is a set of prime numbers. Does anybody know what the complement of A would be? Anybody remember what a number is called if it's not prime?
Decepticon.
What?
Decepticon.
No. That's a good joke, though. I like it. Non-prime. Yeah, we actually give that, so you've got it, so exactly right, not prime. We tend to give it a special name, and we say that it's the set of all x in the natural numbers, because that's our universe, such that x is composite. Means it can be factored. And, of course, we have to add one more number into this set. Or 1. 1 is neither prime nor composite.
Why is 1 not prime?
Good question.
Because it needs a second one in each to be able to be divisible by some number and one. And
No, for, up until a few hundred years ago, 1 was considered prime for precisely the reason you think. It can only be written as the product 1 times itself, right? We can't factor it. But there's this, we're going to get into this more in like chapter 5, I think it is. But in number theory, there is an uber important result. We call it the fundamental theorem of arithmetic. And the fundamental theorem of arithmetic says if you take any positive integer, it's either prime or you can factor it. You could factor it as the product of primes in a unique way. In a unique way. So 12 is not prime, but it's 2 times 2 times 3. There's its prime, up to reordering the primes, right? But it's 2 2s and a 3. That is what defines, that's like the fingerprint, that's like the molecular structure of 12 as a number. But if 1 is prime, then the factorization is no longer unique, because then it's 2 times 2 times 3 times 1, and 2 times 2 times 3 times 1 squared. Every number would have infinitely many factorizations. The integers are what we call a unique factorization domain, and that's actually really important and leads to important results. So 1 is just sort of a special number by itself.
And because of that, because it can't be made up of other primes, since 1 isn't a prime.
It's not composite
itself.
either, yeah. Mm-hmm.
Oh, okay. Cool.
Other operations are binary operations in that they take 2 sets, combine them in some way to perform another set. So the 2 basic, like fundamental operations, the first one is the union. So I'm going to just sort of show you what a union is visually. The way it's defined is the A union B is a set of all x such that x is in A or x is in B. And whenever you see or in mathematics, unless they specify otherwise, this always means or both.
Just like the truth tables.
Yes, just like the truth tables. The or has the same meaning that or has in propositional logic. So if I were to sketch this out, we're going to do more with Venn diagrams in a bit, but here's like a basic 2 set Venn diagrams. Here's my set A, here's my set B. The union is just put them together. Like if you're anywhere in the shaded region, you're in the union.
So you were saying earlier that it would be bad form to create a set where you repeat a characteristic of that set.
Mm-hmm. Like an
So if
element.
A and B both have 1, you don't need to add.
Right. If you were listing out the elements, you wouldn't add it. You wouldn't write it
You
twice.
just add whatever ones A doesn't have and B does have.
Yeah. Like, so, in fact, that's one way to list out elements in a union. I'll be like, oh, I'm going to start, I'll just go to grab all the elements of A, and then I'll scan B for things that are not already in A, and then throw those in. The other sort of fundamental operation that we have for 2 sets is the intersection. And in order to be in the intersection, you have to be in both. So the and really means the same thing that and means in the propositional logic. Like both propositions have to be true for P and Q to be true. The element has to be in both A and B at the same time in order to be in the intersection. So there's the intersection. If 2 sets don't overlap at all, if the intersection of 2 sets is empty, we say that they are disjoint. So there's a piece of vocabulary for you. So let's do an example. They give us a couple sets, A and B. What elements do we include in A union B?
7, 5, 8, 2, and 13.
7, 5, 8. So we grabbed everything in A, and then you said 2 and 13 are in B but not in A, so we got to add those in. Yep, perfect. How about A intersect B?
Only 5?
Only
Yeah.
one's common. Okay, yeah.
Yep,
5.
just 5. And notice I'm putting them inside curly braces. I know you're going to write lots of curly braces, and eventually they just look like that, and that's okay. Like, they don't have to look perfect, but you can't forget them, and you can't write them as parentheses.
Violent squiggles.
Violent squiggles will be just fine. Band name called it. All right, so here's some facts we're going to be able to figure out. If I take any old set A and I union it with the empty set, what should I get?
Okay.
Yeah, like I take A, I add nothing to it, I'm still going to have A. What if I take any old set A and I union it with the universe? We get the universe, yeah. If I take something and add everything, I've got everything. What if I intersect a set with the empty set? The empty set, right? The elements that they have in common is nothing. They have no elements in common because there's no elements in the empty set to begin with. And if I intersect a set with the universe, what do we get? A. Yeah. Like when I, in these definitions here for union and intersection, I started with a box that I put the circles in for A and B. The box really is the universe. That's what we think of as the universe. The universe fits in that box right there. Okay. A subset of a set is a set that is properly contained in another set. So, what's that?
Setception.
Yes, setception. That's a good way to think of it. If A is a subset of B, that means that every element, if X is in A, it's also in B. In fact, if we were going to show, and we will, and you will, write some proofs to show that some set is a subset of another given set, you always start by saying, well, let's let X be in A, or whatever this set is. And then you see where that gets you, and then you show that X must be in B, the other set. And if you can show that that's true for some arbitrary element of A, it's true for all the elements of A. So that allows us to conclude that A is a subset. We haven't really talked about what it means for two sets to be equal. I think we have an intuitive sense of what it means for two sets to be equal. They have to contain precisely the same elements. Order doesn't matter. It doesn't matter if we write an element twice, but we know that it's bad form to do so. Another way of saying that two sets are the same, and this is a really useful way to think of two sets being equal, if we're ever going to prove that two sets are equal. Two sets are equal if each set is a subset of the other. If I can show that A is contained in B and B is contained in A, then they must be the same set. And in fact, that's exactly how we show that two sets are equal. If I'm going to write a proof that two sets are equal, I have to write two proofs. It's kind of like an if and only if proof. You know, that required two parts. Showing two sets are equal requires two parts as well. Okay. The power set of a set.
Oh, that's a fancy P.
Yep, it is a fancy P. The power set of a set is a set. It is a set whose elements are the subsets of the set. I just want to say set as many times as possible in a single sentence. This is always a good way to do it. Define what a power set is. So, what's interesting about a power set is that I'm going to give myself a little bit more space here. What's interesting about a power set is that, first of all, it's a set, but its elements are also sets. So, and the sets that are going to be included are just anything that's a subset of this given set here. So somebody tell me a subset of A. What's a set that's contained in A?
B and C.
So the set containing B and C. So I'm putting curly braces around that.
Oh boy. Set containing A and B,
Yep,
and set containing A and C.
great. I think those are all the doubles, right? Or the pairs that we can take.
Oh. And then a set including just A, just B, just
Uh-huh,
C.
yep. So those are the singletons.
You repeat A, B, C as a set?
Yep, the whole set itself. We're missing one.
Set of nothing.
the empty set. The empty set is a subset of every set. And the reason is because you can't find me an element in the empty set that's not also an element of any other set. It's something we would call kind of vacuously true.
Say that again?
You can't find me an element of the empty set that isn't also an element of this set A. So it is,
Gotcha.
yeah. How many did we find?
3.
How many subsets?
8.
8. That's how I know we're done. We got to 8. I was like, we got them all. I know there's going to be 8 subsets. The number of subsets, so if I don't know if we've defined this yet, but the size of a set, maybe I'm getting ahead of myself, but I don't care. The size of a set, I'll do this up here. The size or cardinality of a set A is denoted like that. We put the bars around it like absolute value signs, and the size of A is just the number of elements in A. So, I'm going to scroll down here. If the size of a set A is n, like if A has n elements, then its power set, size of the power set is 2 to the n. So in this case, A had 3 elements, and we found 8 subsets. And that is 2 cubed. So once we got to 8, I knew we were done. The reason that's true is if we think about, we can draw a parallel between subsets of a set with 3 elements and like a bit string of length 3. So if I'm picking subsets, right? If I'm just trying to make a subset, I think of it as making 3 choices. A choice for A, a choice for B, and a choice for C. And I'm either going to include A or not. So that's 2 choices, right? 2 options. And then I move on down, and I can either include B or not. So I've got 2 options. And I move on down, I can either include C or not. And by using what we call the multiplication counting rule, we get 2 cubed or 8 subsets. How's that? Good? No? Are we suspicious?
It's okay.
It's okay. Let's get more excited, you guys. It's not like 8 in the morning, right? You can't claim like that it's just too early.
It's gray out though.
Too early.
It's gray out for,
But like we have the nice bright fluorescent lights in here.
It's January, it's too early.
Yeah. It's almost nighttime. It's January.
Hibernating right now.
Yeah. All right, so some properties of sets. Both union and intersection are commutative. What does commutative mean?
Beginning of each other.
Nope. I think you're thinking about distributive.
Yes, that's what I was thinking of. The third one. Hey.
The third one, yeah.
Commutative, doesn't that just mean that it doesn't matter what order they are?
Yes. So if the union is commutative, that means A union B is the same as B union A. And the intersection is commutative, means A intersect B is equal to B intersect A. Union and intersection are both associative. Does anybody remember this one? This one's a little bit, maybe not as obvious. Associative, like as a word, just doesn't ring bells usually. So let's say I want to union 3 sets. Associative means it doesn't matter if I find A union B first and then union it with C, or if I first find B union C and then union it with A. Notice it's unions all throughout. I'm just changing the grouping. And then the same is true for intersection. Three and 4, we give us the distributive properties. So union distributes over intersection. A union, B intersects C. If that union distributes over the intersection, what does that mean? What should we be able to write on the other side?
A union B,
Distribute.
In parentheses?
yeah.
Yeah.
parentheses, and then, the other sign. which I-
Intersect.
And then A union C.
Yeah, great. And then intersection distributes over union, so we get to do the same thing there. A intersect B union C is A intersect B union. What's going on out there? A intersect C.
Having too much fun.
I guess. What should happen if I take a set and union it with its complement?
It vanishes.
Have
Mm,
the universal set. If
yeah.
you have-
So which one is it? Who wants to support their answer?
If you have everything in the set and everything not in the set, then that's everything.
Yeah, yeah. So we're unioning them, right? So take everything in A and then add to it everything not in A. You should have everything. Yeah, so this is the universal. So Sam, if I take a set and intersect it with its intersection, what do we get?
Nothing. Empty
Intersect
set.
it with its complement, sorry.
Empty set.
Yeah, that's empty. Right? If I take, like, the elements that are both in A and not in A should be empty. Right? If there's a set that, if you think you've found a set where there's an element that's both in the set and not in the set, then that's not a well-defined set. It's not a set at all. Okay? Remember, in order to be a set, there has to be no ambiguity about what's in it. All right, now we get De Morgan's laws. We saw these in the logic section.
It was mentioned, yeah.
Yeah.
In the practice homework.
Mm-hmm. Oh, yeah, right. So we have De Morgan's laws for sets as well. And so what De Morgan said in the logic is basically is what it says for sets. It says you can sort of kind of distribute that complement over a union, but you actually have to flip the sign. So it doesn't actually distribute, but it's sort of what we hope that it would distribute. You know, we want to. There's like an urge to distribute everything, I think, in mathematics. With De Morgan, it says we can sort of kind of distribute, but we got to flip the sign. So the complement of A and B is A complement intersect B complement. And the complement of A intersect B is A complement union B complement. We can use operations to simplify expressions. Or use these properties of operations to simplify. So let's say we want to simplify this expression. A intersect B complement and then intersected with A. So if we use De Morgan first, we can rewrite that first part as A complement union B complement, and this is intersected with A. And I use De Morgan. Notice that I'm supporting each step with a reason. It doesn't have to be a sentence. I'm just citing like what property I'm using. Now, I guess this next step could be skipped, I guess, but I like doing it because of how I think about distributing. I'm going to use the fact that the intersection's commutative. I'm going to use the fact that the intersection is commutative. So if I'm going to use the fact that intersect is commutative, what is my next line going to be? What does commutative mean?
It means it doesn't matter what order it's in.
Uh-huh. So that just that the intersection of two things, doesn't matter what order. So what two things are we intersecting?
A complement, union B complement, and A.
Uh-huh. So what's my next line gonna be?
Flip it around.
Yep. So what am I gonna start with?
A intersect,
Mm-hmm.
A complement, union B complement.
Mm-hmm. Great. Now I'm intersecting the set A over that union. What could we do?
You can distribute it.
Mm-hmm. So we're going to use the fact that intersection distributes over union. So then what would that look like?
B. A intersect A complement union A intersect B complement.
Mm-hmm. Anything we can do now?
Maybe A intersects A complement
To be what?
well, to the nothing.
To nothing, to the empty set. Yeah. So there's no elements in common in A and A complement. So that's the empty set. Union A intersect B complement. So this is, we're using the fact that just A intersect A complement is empty. Now what?
We can eliminate the anti-set,
Mm-hmm.
because anti-set union something is the other thing.
Yeah. So what's on my next line?
A intercept B complement.
Yeah, and that's because the complement union any set, I'll just call it S, is S for any set.
Sorry, what was S?
I'm just an arbitrary set.
Okay.
So in this case, the thing playing the role of S is A intersect B complement. How's that? And that's simpler. I think that's as far as we can get. It's stuff in A that's not in B, right? A intersect B complement. Are there questions on that example? Okay.
Looks like you just moved the parentheses inside or the complement inside the parentheses.
Looks like you could move, like from
From
the
where we
beginning?
started.
Well,
Where we
yeah,
started,
I mean,
very similar.
it's sorta, only we had more involved there, right? We had a bunch of stuff intersected with A. I guess in that there's a single complement and just the sets A and B, but Let's look at some more set operations. The set difference of A and B is denoted with a little backslash, kind of like, some people actually use like a subtraction sign. That's less common than just the backslash, but the set difference is you take A, you take the set A, anything that's in A that's also in B, throw it out. Like throw out the intersection, anything that it might have. And we'll note that the set difference is not commutative, right? If I start with A and throw out anything that's in B, I'll probably get a different set than if I start with B and throw out anything that's in A. I think I would, in fact, I would have to get a different set. The symmetric difference is denoted with a like triangle B, delta, yep. And in some texts they use a little circle plus, but the delta or the triangle is more common. And it's the union, you could think of it as, you could define it in terms of the set difference. It's the union of the two set differences. A set minus B, union with B set minus A. But it's also, the more intuitive way to think of it is, it's stuff that's in A or B, but not both. It's the exclusive OR for sets. And then we'll note that in the operations in A and B give you another set in the same universe, right? So if I take everything in A and throw out B, I'm still in the same universe, right? The same overall set of elements. The next one gives us a new type of set. So when we make the Cartesian product of two sets, we denote it with a little kind of cross times there. It's a set of ordered pairs. Note the parentheses around the pairs in the set. It's a set of all ordered pairs such that the first element is in A and the second element is in B. So the order matters. Let's do some examples. They've given us 3 sets, and we want to find first the Cartesian product of A and B, or A cross B. So it's a set of ordered pairs. And it's going to be just ordered pairs where the first coordinate is in A and the second coordinate is in B. So somebody tell me something that's in an ordered pair that we're going to include.
1 alpha.
1 alpha. Yep. In fact, there's other ones I could pick with the first digit or the first coordinate being 1, right? I could do 1 beta. What else?
1, I don't know what that symbol is.
It's a gamma.
That's gamma?
Yeah.
It would have to be 1 gamma.
What else do we get?
1 delta? No, that's in C.
That's one's in C, yeah.
And you can repeat the process starting with B. Because they're ordered, so it matters what order they're in, right?
Yeah, we could restart the process starting with what?
Starting with alpha.
2 alpha.
2.
2.
The first coordinate has to be an A.
Yeah.
Right, so those are all the ones where the first coordinate is 1, which is an A. So, and those, we've exhausted all the second coordinates we're going to get there. So we just repeat that pattern. So we have 2 alpha, 2 beta, 2 gamma, and then again with 3. What about the Cartesian product of B and C? What's something that's in there?
Alpha alpha.
Alpha alpha. And so the doubles is included. That's a single, the ordered pair that doubles alpha alpha is a single element. So we're not violating the rule where we can't list an element twice. Alpha alpha as a double is a single element of this Cartesian product. And then what else? Alpha lambda, yep. And then alpha delta. And we can do the same thing starting with betas. So beta alpha, beta lambda, beta delta. And then with gamma, gamma alpha, gamma, beta. Oh no. Gamma, alpha, gamma, lambda, gamma, delta.
No
Yeah.
frat names?
What's it? Yeah. Yeah. Yes.
Could you use the dot 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 in this so that you can find a pretty clear pattern? from
I
the
mean,
larger ones?
I wouldn't. If you're asked to list the elements, you should list the elements. If we know what sets B and C are, I mean, here's the pattern right there. Right, it's just saying B cross C. If they were like infinite sets, we would definitely want to do something like that, or just describe it. But if you're asked to list out the elements in a Cartesian product, you should do that.
Like the previous ones we were doing, where, like, you're done when, however the first
Oh,
one's
yeah.
squared. Is there
Yeah.
something like that for this one?
Yeah.
Where you know when you're done?
Yep. Is there a pattern to like how many we should get?
Well, you should theoretically have the square of, you should have the first one to the exponent of however many is in the second set.
Not to the exponent.
Times the number of.
Times, yeah. Just multiply the two sizes. Like these Cartesian products, when these elements, we call them like coordinates, and we do that for a reason. So you could almost think of like,
That's why we have 9, 'cause 3
let's say we have B. B had the elements alpha, beta, gamma. And C had the elements alpha, lambda, delta. You can just sort of make a little grid. Each one of these dots is going to correspond to, here's our alpha, 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 beta. And we could see like the number of rectangles that we form in the grid is this size times this size. So the size of the Cartesian product, the number of ordered pairs, is just the number of elements in A times the number of elements in B. Let's do this set. Let's find the set difference. B set minus C. What should we include here?
Beta and gamma.
Beta and gamma, because B contains alpha, beta, gamma, but C contains alpha, so we're going to throw that out. And then the last one is the symmetric difference of B and C. So remember, think of that as the exclusive OR. So I'm going to go back up so we can look at these sets. We want all the elements that are in B or C, but not both. So I'm looking at these two sets.
So it'd just be
beta,
lambda.
lambda,
Yeah, beta lambda delta.
delta,
And gamma, I
and
think.
gamma, yeah.
Yep.
Everything but alpha.
Yeah. So beta, gamma, lambda, delta. Questions? Okay. Then, let's keep going. So Venn diagrams, we already saw a little bit what a Venn diagram is. So it's just a kind of an abstract way to visualize two sets. When you're drawing like a generic Venn diagram, we've seen the one for a Venn diagram for two sets and where we allow for the overlap. Here's a Venn diagram for three sets. Really, I should include the rectangle because that's the universe. But you want to allow for all possible intersections, which is why in that three-set diagram, all possible intersections are allowed for there. You don't want to draw it like this because that doesn't let, A intersect with C, and it doesn't allow all three of them to intersect together. So some of the intersections in this diagram here, in a given situation, it's possible for some intersections to be empty, but we want to just allow for all possible intersections. I think using a Venn diagram can be a great way to, like if I'm working on simplifying a set, like we did here, we use properties and maybe I'm stuck and I'm not really sure where to go. If I can use like a Venn diagram and shading to kind of figure out what region I'm talking about, it might help give me ideas for like how I might go about either simplifying the expression or writing a proof about two sets being equal or containing, one set being contained in another. It gets me to what I like to call the I believe it stage. And then I feel like I have more confidence, like, okay, I believe that it's true, I should be able to show it. So we're just going to draw some Venn diagrams and indicate each of these regions. So A set minus B. So I'm going to have a Venn diagram that allows for two sets. Here's A, here's B. What is the region A set minus B? Where is that located?
Just the side that A is on its own.
A on its own?
Yeah.
So like this part here?
Yeah.
Yeah. So it's all the stuff in A that's not in B.
Can you left-handed?
Yes. A union B, we kind of actually already drew this one when we were doing the definition. But what are we going to shade here?
A union B is the middle, right?
It includes the middle. Well,
Everything in A and B.
Yeah.
okay, so everything in it that's so
So both circles, including the together.
both circles includes great. I wanted like a visual. Because when you say shade everything, I was like, well, like the whole box, or, and when you say everything in A and B, I'm like, A and B, isn't that just where they overlap? I learned to be like more careful with my words as a student of mathematics. Because like everything means something, we try to be like really explicit. Okay, the symmetric difference of A and B.
Guess what's in the middle?
What's that?
Guess what's in the middle?
Well, that would be the intersection here.
Anything except the middle?
What's that?
Anything except the middle?
Like,
Including the circles that
oh, everything in the circles that's not in the middle. Okay, right, so remember the symmetric difference is the exclusive or. So to be in the symmetric difference of A and B, you're going to be in A or B, but not both. I like Venn diagrams because they can help solve counting problems. So we're going to do a counting problem or two next. So here's a problem. It says there's a class of 200 students. 120 of them are taking history of kickball. 110 are taking lolcats in pop culture. I'm pretty sure both of those would be an arts and humanities elective, maybe. Maybe history of kickball could be social sciences. But, and then 80 of those lucky students are taking both courses. And we want to know how many students are taking only one, but not both of the two classes, and how many students are taking neither. So, the history of kickball, I'm going to call that, the students taking history of kickball, I'm going to call that K. And the students taking lolcats and pop culture, I'm going to call that L.
I knew you were going to call it L.
Did you?
Predicted.
Yeah, successfully. I'm going to make a little Venn diagram. So here's all the students taking lolcats and pop culture. They go in that L circle. All the students taking history of kickball go in the K circle. If you're using a Venn diagram to help you count things, and by counting, I mean not just figuring out how many, not just necessarily answering a question, but I think about accounting, making sure everything's accounted for, and I'm not double counting anything. So if I'm using a Venn diagram to help me count things, you always start in the middle and work your way out. Because, yeah, there are 110 taking lolcats and pop culture, but I don't know, like, that means in the whole L circle there are 110. So what I do is start on the inside. 80 of them are taking both, so I know for sure there's 80 students there. Now, 110 are taking lolcats and pop culture. I've already accounted for 80 of them in the intersection. How many are left? 30. And so those are the ones taking lolcats and pop culture that are not taking history of kickball. So that 30 goes there. There are 120 taking the history of kickball, but we've already counted the 80 of them, the ones that are taking both.
40.
So now there are 40 left here. And now there's one region that we haven't accounted for. That's the students that for some reason maybe are taking neither of those two courses.
Universe.
What's that?
Universe.
Well, how big is the universe here? 200, right? Of the 200 students. So how do we figure out what goes outside?
Whatever's left.
Whatever's left. Yeah, so what is left? Anybody do that?
50.
Because you have 70 plus 80, which is 150.
We have
I got you, bro.
70, oh yeah, 70 plus 80, so there's 50 out here. Okay. Good. So now let's answer the questions. How many are taking one but not both?
70.
Yeah, and you got that by looking at what?
Looking at what is just in L and what is just in K.
Yeah, so in fact what we were doing was looking at the symmetric difference of K and L. And you determined that was 70. How about taking neither?
50.
And if I wanted to denote that set in using set notation,
Would be the was it inverse of L and K?
complement.
Complement.
So there's a couple different ways we could write it, but we have to be careful. So in order to be taking neither course, that means you're not taking history of kickball
Mm-hmm.
and you're not taking the lolcats course. Intersection. Another way of saying that is you are not taking kickball or lolcats. So that's the same as being outside the union. So visually, outside the union kind of makes sense, right? It's the stuff that's outside, like the MasterCard logo, the two circles. The other way we have to think about it, double shading. If you're in the intersection of two sets, it's where you shade both regions. If I were to shade K complement and L complement, then I see where I've shaded twice, and that's the intersection. But the fact that those two sets are the same, what property is that? Like the fact that,
Associative.
nope. The fact that those sets are the same, it has a special name. Or I guess it's a property, it's a law. De Morgan, yep. That's De Morgan. Let's do one more. Are there questions on this one first? Okay.
Why do you use the pipes on either side of?
Number of the size of that set. Yep. Okay, so here we have a lot of facts here. So there's in a group of 96 students, the following statements are true.
And 96 is the universe.
So 96 is the universe. Or these 96 students. That's our universe here. 43 live on campus. 38 are women, 18 are seniors, and then we have combinations of these. Seniors that live on campus, senior women, women that live on campus, senior women that live on campus. We have questions we want to ask, but I feel like we should organize this information. Yeah.
First question. So that's 7 groups?
It looks like 7
How
groups.
would you do a Venn diagram of that?
3 groups.
It's only 3 because the other ones are combinations of them.
Ah,
Right, yeah, good. So,
I still wanna know how you do a Venn diagram.
well, it's like, you kind of, I don't, you know what? Like,
Spirograph.
yeah, exactly.
Oh.
You use a spirograph and then, you
You
know,
gotta do it big so people can read it.
yeah. Okay, so we need 3 sets. Okay, so women. I'll call that set W. Seniors. I'll call that set S. Living on campus, I'll call that set C. Living on campus, women, seniors. If we're filling in numbers to help us with counting, where do we start?
The middle.
Right in the very middle. So the last thing they told us was that
6 senior women live on campus.
6 senior women live on campus.
6.
I'm gonna zoom out and try to see if I can see the facts. Okay. Now we're gonna zoom out and do the other intersections. So let's say we do, let's see, this one down here where S and W intersect. What number should go there?
10.
Close.
Senior.
10 senior.
10, there are 10 senior women. 6 of them live on campus. We've already counted 6 of them, so 4. Good.
Tricky.
How about the one at the top? Women on campus.
1.
1, because we've already counted 6 of those. And seniors that live on campus.
1.
Yeah, 5.
Why 5?
Because 11 seniors live on campus.
Yeah.
and 6 on-
And we've counted 6 of them. Does that make sense?
Yeah, I was looking at the
Oh,
wrong
okay.
thing. I was looking at 10 are senior women.
Uh-huh.
so-
Oh, yeah.
Oh, if there's 11 on campus and 10 of them are women. Then
Oh, right, yeah. All right, now let's do the other ones. Let's start at the bottom for seniors. There are 18 seniors.
So
3 left.
Yeah,
5 plus 6 plus 4
there's 15, and then there's 3 left. Yeah, good. How about the women? 38 are women.
27.
27, because 10 are accounted for there. And 43 live on campus. 31, because there's 12 accounted for there. And then what about on the outside?
out of 96.
Yeah, so all the numbers have to add. So I take 96 and I just subtract all these numbers we put in there. And when I did that earlier, I'll save you the arithmetic, I got 19. So women that don't live on campus. So that means you have to be in the W circle and you can't be in the C circle. So that's W intersect C complement.
Is that the same as W with that backslash C?
Yes. Yep. W set minus C. Yep. So if you're not in the C circle and you are in the W circle, I think you have to be one of those in one of those regions. So that's 31. Senior men.
So it would
Seniors that aren't in.
It'd have to be an S.
be-
So
Can't be
there
W.
can't be in W. So we could also denote that as S set minus W. And so that would have to be, you're in the senior circle, but not in W, so I think that's those two.
Or plus the 19, right? Because, or the senior.
Yeah, the 19 are not senior. So I think we just get those, and that's 8. How many non-senior men do not live on campus? What are we looking at here? Non-senior, so you have to be in S complement, and non-senior men, so you have to be in W complement. Do not live on campus, have to be in C complement. So you can't be in any of the sets.
So you're just the leftovers.
So you're just 19.
Yeah. Mm-hmm. I'm going to update this problem for the, stop using outmoded language that presents a gender binary. But other than that, we got the counting down.
If we were to do that with the backslashes,
Oh, I don't know. I guess,
it doesn't.
I mean, you could, I don't think I would do that with the, because we're defining it only by what it's not in.
We're finding everything.
Like, there's nothing, yeah. We could say that it's also outside of the union of them all. So we couldn't do it with the set. I don't know how we would do it with the set minus, but we could say that it's a complement of the union,
Okay.
unions of them all.
So you would never write something like that, like, you would always write it S union W union C, you'd never just SWC in parentheses?
What do you mean like this?
Yeah,
That's not defined.
okay.
That would define a set of SWC.
Yeah. Yeah, we have to indicate the operation. Yeah, there's not an assumed operation. With sets, there's not an assumed operation if we write nothing in between them,
Unlike multiplication.
unlike multiplication. In some areas of mathematics where we look at special kinds of sets with different properties, you might define a set like AB, and it will be like, oh, if you put all the elements AB together, like maybe there's an operation defined between the elements, and then you see what you get when you mash them each together, and then you put those in a new set. So there are different areas of mathematics where that type of operation is defined for special kinds of sets that satisfy properties, but not in an abstract like set theory. All right, so I think we're just about out of time. We will write a proof about sets next time. Are you excited? Yeah? Okay.